another organic chemistry intro lecture. Can the folks online hear me on TikTok Live? Can you all hear me? Just want to make sure you all can hear me as well. I know the folks on the Zoom can hear me. So just waiting to hear. Can anyone comment in the chat that they can hear me on the live? Yes, perfect. Thank you all so much. Well, welcome, as I was saying, to a bunch of folks on the Zoom. This will be a nice little lecture that I'm going to try to wrap up some of the intro stuff. And that's because I'm going to try to give you all a quiz slash exam on Tuesday. So on Tuesday, expect to have to be evaluated on your knowledge. So come with a pen and paper and pencil, whatever, and I will post the quiz, and we're going to do some self-grading and make sure you post, or share with everyone the scores you get. Okay. So what we're going to do is take a little bit of do a little bit of a review of Bronsted-Lowry acids before we move on to Lewis acids and other stuff. Okay, and this is a bit of a challenging concept for most students. What we're doing here is not only are we talking about acid and base reactivity, but we're also learning how to draw arrows. Okay, and so arrows are very important in organic chemistry because what we're doing with arrows is we're showing the movement of electrons, and how electrons move is a critical thing to learn so you can showcase molecules reacting with each other. So once again, the Bronsted-Lowry definition is that an acid donates a proton or a hydrogen atom, H+, and the base is the molecule that accepts that proton, H+. We're going to refine this definition, but this is the one that you typically learn in high school, and it is what we're going to start with. So the first question is, how do you identify the base? We have two molecules here. Here's an example in A. How do you identify the base? Can someone tell me? How do you identify the base? Which one is the base in this molecule and why? Anyone give me a bit of an explanation? The one on the left. Why is that the one on the left? Because it's negative, exactly. The negative atom, typically when we see an atom that's negative, that's going to be the base. So if you see one molecule with an atom that's negative, that has a lone pair on it, that's probably going to be the base, okay? Now we're simplifying a lot of this. It's not always the case, but for the most part, it'll be the base. And so that means this one is the base, which means the other molecule is the acid, okay? So this is the base. This is going to be the acid. And then we talked about how we would draw our arrows. Now, this is electron rich. We're going to be sharing electron density, that lone pair, with an atom in the acid. The base shares an electron with the atom in the acid, and it's going to share it with the H, because by the Bronsted-Lowry definition, the base is accepting an H, and the acid is donating an H. The question I have for you is, which H in the acid, which hydrogen atom in the acid will you be going after? Which one will be donated and accepted? There are 6 hydrogens. The one next to the sulfur, okay, very nice. And that's because sulfur is more electronegative than carbon. And so sulfur is pulling its electron density. The electron density it shares with hydrogen closer to itself. So that bond between sulfur and hydrogen is very weak. It's not as strong as the bond between carbon and hydrogen. Their electronegativity difference they're very similar in electronegativities. That difference is very small. And so they're going to form, in this case, a better bond. So the hydrogen next to the sulfur is the weaker relationship. And so with that in mind, we can entice this hydrogen by sharing those electrons with the hydrogen, okay? So the atom with the lone pair, the negatively charged atom, is sharing its electrons with a hydrogen because the hydrogen is losing electrons to the sulfur. So the next question is, can we just share with the hydrogen? The answer is no, because the hydrogen can only accommodate 2 electrons at a time. It's currently sharing with the sulfur, which means in order for it to accept the lone pair from the carbon, it has to lose that connection it has with the sulfur. And so we have to show that the electrons that are in that bond, and remember, every time we see a bond is really just two electrons, right? So every line is equal to two electrons. So a line is equivalent to two electrons. So anytime we see that, we know that. So therefore, we know when we move the electrons from the bond, what we're really showing is that those two electrons are going on to sulfur. All right, let's draw what that looks like. I'll give you all a minute to draw the result of that acid-base reaction. So get your pen, your paper, and draw that and see if you can come up with the right answer. I'm going to draw it in 30 seconds. Okay, so let's draw the product of this reaction. We just said that the base is going to share electrons with the hydrogen, which means now it's the one that's making a bond to the hydrogen. So that carbon, instead of having the electrons to itself like it had before, those electrons are now going to exist in a bond, in a shared relationship with the hydrogen that it just took. Does that make sense? Let me try to draw this a little bit better. My handwriting is deteriorating over time. So you can see that the hydrogen, this is the one we just added, right? And the electrons that the carbon had are still there. They're in that bond, okay? And so what happened now to the sulfur? The sulfur is now going to have one less hydrogen atom. And so we must have a result that looks like this. And we also gave two more electrons to the sulfur, right? We just donated two more electrons to the sulfur because sulfur had two and now it has four to itself. So can someone tell me the formal charge? Remember a formal charge, we can calculate formal charge, right? By looking at the valence electrons of sulfur, which we get from the periodic table, and we can minus the sticks and the dots. That's our shortcut that we talked about. So how do we, if we subtract the sticks and the dots from that, what's the valence of sulfur? It is 6 minus 1 stick minus 6 dots. That's -1. And so we put a negative charge next to the sulfur. And so that is our acid-base reaction. We can also name the molecules on the right-handed side of this equilibrium. This would then become the conjugate acid. We name the ones on the other side the conjugate. And this would be now the conjugate base because that's now the negative atom on the other side. Okay? So you always have a pair, an acid-base pair on either side of the equation. And the one, of course, that has the negative charge, generally speaking, is the one that's going to be the base. Any questions before we move on to do another example? I want to make sure you all really understand join your acid-base reactions. This is an equilibrium. And if we wanted to continue on with this, we could use structural indicators or acidity tables or pK tables to make an argument for which side of this equilibrium the reaction would lie. I think we're going to skip this for this intro course, but we could decide which side of this equation the reaction lies. Any questions before we move on? Does this make sense? Great. All right, so now it's your turn. I'm giving you a really cool molecule. This is Prozac. If you didn't know the structure of Prozac, now you know. And I'm reacting it with H3O+. Anastasia, yes, the reaction many times will be reversible, and we can decide that actually. We can use a lot of arguments to decide whether it's going to be reversible or it's going to be go forward in one direction or the other. But we're going to skip that conversation. That requires a little bit more knowledge for us to have that conversation. So here is Prozac and here is H3O plus. The question once again is which one is the base and which one is the acid? Let's try to determine that. I'll give you 10 seconds. This is a little bit different, right? We don't have an atom in either of them that is negatively charged. So we're trying a different kind of an example here. So which one is going to be the acid? The one on the left or the one on the right? What do people think? Yes, H3O plus is an acid, mama. Yes, Isaiah, thank you for that. Yes, and generally speaking, if you have the molecule that's positive, will probably be the acid, and if you have a molecule that's negative, that's probably going to be the base. That's a simplistic way of thinking about it, and kind of the questions I typically ask for intro folks. I would make it more difficult than that. But now we have a problem, right? We have to decide which atom in the molecule on the left in Prozac is going to be acting as the base. So yes, this is our acid. And by the Bronsted law redefinition, we know it's one of these H's that we're going to take, right? One of these hydrogens we're going to take. So on the left, which atom is the atom that's going to engage this hydrogen? That's the million-dollar question. Is it the oxygen or is it the nitrogen? Let's draw in our lone pairs. Remember, when we draw these reactions, the reactions are coming from the lone pairs on the atoms for the most part. And so we have two lone pairs on oxygen. What other atom has a lone pair? Nitrogen also has a lone pair. That's correct. All right, so it's probably one of those atoms, right, that are going to use their lone pairs, a lone pair to attack the hydrogen. So which one do we have the more faith in? Is it going to be the nitrogen atom or the oxygen atom? Let's be careful. The lone pair is on the nitrogen. Hydrogen only makes one bond, so it's very happy right now as is. So yes, the oxygen is more electronegative, but what does the electronegativity mean for the basicity? Remember, a base has to accept a hydrogen. And so which one is going to want to accept the hydrogen more? The oxygen is more electronegative, which means it's going to be holding on to its electrons and it's not going to want to share them as well, right? So it's going to be the nitrogen that shares them because the nitrogen is less electronegative. It's not holding on to the electrons as much. It's more willing to share them with the hydrogen. So this is different. We haven't talked about an example like this, right? If you have multiple atoms that you can choose from, the one that's most basic is the one that is less electronegative, okay? The one that's more basic is going to be the one that's least electronegative. And that's because it doesn't want to hold on to its electrons as much. And so because of that, we can draw a mechanism now from the nitrogen atom that will attack a hydrogen, any one of these hydrogens. And of course, as we argued, you have to break the bond. By the way, the oxygen also has a lone pair that we didn't draw in. It was already there. It needs to have 8 electrons. And so you're going to break that bond to oxygen. And just like that, we will have a product on the right-hand side. And we can draw this product. It'll look like this. The oxygen did not participate in this reaction, so we will draw it back and leave it the way it is. However, the nitrogen now has 2 hydrogens attached. It had one before, and now it used its lone pairs to get another one, which means it must have a formal charge of positive 5 valence minus 4 sticks. And then, of course, the other product is now oxygen with 2 hydrogens, and it gained a lone pair from that bond that we just saw, that we just moved. That's the pair of electrons that ended up on the oxygen with the other pair. And so we can label these, okay? This is our conjugate acid now. And this is our conjugate base. Okay. Any questions about that one? Are we getting the gist of this? Does this make sense? Ah, good question. Why do I draw an arrow away from the NH? Because I'm always drawing the arrow from the lone pair. Let's make sure we understand that. Here is the lone pair on carbon that is reacting with the H. Here is the lone pair on the nitrogen atom that is reacting with the H. So if you look at these two problems, you can see the similarities, right? We're always drawing the arrow from the electrons, from the atom that has the electrons. It's the electrons that are moving. And we're going to talk about that shortly. But we have to start our arrow from the electrons, from the atom in the base that is sharing the electrons with the hydrogen in the acid. So if you look at these two problems, the arrows actually make sense. They're very similar. Whichever one is the base, you're going to start your arrow from that lone pair on the base, and the arrow must end up at the hydrogen. Yes, the base becomes the acid, and the acid becomes the base on the other side of the equilibrium. Yes, I'm showing where the electrons go. That's exactly what it is. We are showing where the electrons go. And yes, this would be a deprotonation. That is another way of describing what's happening. We are deprotonating the molecule on the right. The acid is getting deprotonated. It's losing its proton. Okay, so these other two problems are on the drive with the folder. Why don't we do one more in the interest of time? I'm going to skip to D. This is another favorite molecule of mine, ibuprofen. You can take, if you take Advil, you are taking ibuprofen. This is the structure of ibuprofen. And therefore, based on your understanding of acids and bases, what would you describe ibuprofen as? Is it a base or is it an acid? Ibuprofen is an acid, and you can see there's an H there that's attached to an oxygen. It's giving acidic, right? So ibuprofen is an acid. We also know this from last lecture that this here is a carboxylic acid functional group. Remember, we talked about functional groups last lecture. So that's a carboxylic acid. Great. So let us label them. This is our acid, and this is our base. I gave you a very straightforward one. You can see the negative charge on the carbon. And now you all are experts. You know exactly what to do. This carbon is going to take this H because it has lone pairs. And then this bond has to break and give electrons to that oxygen. As I mentioned before, I don't always draw the lone pairs in an oxygen, but we should know that oxygen must make two bonds and two lone pairs in its neutral state, right? It has to have 8 electrons, and it makes 2 bonds and 2 lone pairs. As we move through the course, we often leave the lone pairs behind because we know they're there. But for now, I will try to remind myself to put them in for those who still need to remember that it's there. Now, the small arrow has to be drawn because if I give electrons to the hydrogen, I have to release those 2 electrons in this bond. There are 2 electrons in this bond. Hydrogen cannot make 2 bonds at any given time, right? So if I'm giving it electrons from the carbon to make a bond, right, I cannot still hold on to those electrons. Those electrons have to be released because every time we draw hydrogen, it's always making one connection, right? And so what we're saying with the small arrow is if we're given electrons from that carbon to that hydrogen, we also have to release the electrons that hydrogen currently has. You can't hold on to all 4, right? You have to let it go, right? Let it go, like frozen. So it's being let go to the oxygen. Does that make sense? Okay. And if you notice that we do that once again, let's go back. We do that every time. We always have that second arrow. If I give electrons to the hydrogen, I have to release those electrons. If I give it to the hydrogen, I have to release the ones that it's currently holding on to. So let's draw the product of that. Here is my outcome. And I would now have, ignore that darkened line, we'll talk about that at some point. Now the oxygen has 3 lone pairs. Those electrons in the bond are that bond is a pair of electrons. So when we move them to the oxygen, they're just being shown as a lone pair. So now we have 3 lone pairs. And then, of course, the other thing we have is the carbon on the other side is now the one that has the H. And those are the 2 answers, right? H has to release them because H can only make 1 bond. Remember, we talked about this, if you weren't here in the first lecture, if this is a hydrogen atom and this is a nucleus, only 2 electrons can be held in the first orbital. Only 2 electrons can be held. You cannot have more than 2 at any given time in that orbital. So that's kind of hydrogen's max is 2. Okay. That's why right now hydrogen's making 1 bond. That's 2 electrons. So only 2. So this is the conjugate base. And this is the conjugate acid. Okay. Fantastic. You guys, I think, are pretty good. This is your homework. Do this one on your own. Let's see what you come up with. All right, we're going to move on to talk about Lewis acids and Lewis bases. Okay? Yes, we just had a base donate electrons to an acid in ibuprofen. That's exactly what we did. All right, let's talk about Lewis acid, Lewis bases. Now, I like Lewis acids and Lewis bases more, and that's because it's a broader definition of what an acid and a base is. As we've been talking about, and the main difference is this, I should say. The main difference is which atom is accepting, or how we define the atom that's accepting the electrons, okay? The atom that's accepting the electrons, it's always been a hydrogen. That's by definition, a Bronsted-Lowry acid is an acid where the hydrogen is accepting electrons. Every time we draw Bronsted-Lowry acid, we're giving electrons to hydrogen. So HCl, right? If we have a base, say OH minus, we're giving electrons to this hydrogen, right? If we have sulfuric acid, here's another acid that we talk about a lot. Here's sulfuric acid. This is giving electrons to a hydrogen. So the identity of the atom that accepts the electrons in a Bronsted-Lowry acid-base reaction is a hydrogen. You're always giving electrons to a hydrogen. Does that make sense? We've been doing that. That's a simplistic way. Lewis acid and Lewis base broadens our understanding of what atom can accept the electrons. Basically, through this definition, it allows for us to give any atom that needs the electrons the most to get it. And it doesn't have to be an H. Now, for many students, this is a lot harder because with the Bronsted-Lowry problems, you're just looking for a hydrogen. You're like, well, which hydrogen is getting it? You already know it's a hydrogen. But Lewis acid base makes it a little bit more challenging because you have to think more clearly and carefully about which atom you're going to give the electrons to. So of course it's a harder problem. But I think it's actually quite easy. If you think about the fact that the reason we give the electrons to the hydrogen is because it's in a bad relationship. It's in a terrible relationship, typically. A very strong acid will just have a hydrogen in a terrible relationship. HCl. The Cl is extremely electronegative. It's pulling electron density from that hydrogen real hard, right? Hydrogen is almost lonely. And then sulfuric acid below, that oxygen is pulling it real hard. As a matter of fact, you can think about it as tug of war. The oxygen has reinforcement from the sulfur next to it. And the 3 other oxygens in the distance are all helping that oxygen to pull electron density away from that one hydrogen. So this is why hydrogen in these really strong acids is just always the atom you're going to give electrons to. They're in a very poor relationship. So the question is, which atom now in, for example, In this um, scenario, is the atom that needs electron density the most. First of all, which one's going to be your acid and which one's going to be your base? I would say the one on the right is the base. And the reason why I would say the one on the right is the base is because it has a lone pair. I see lone pairs, right? We've used neutral bases before. This is telling me I can use that. I'm looking for a lone pair. Generally speaking, when I give problems, I like to use my acid-base reactions, at least in the intro part of a course, where the base is really using a lone pair of electrons. Okay, so that's the base for me. It has a lone pair. Now I have 4 atoms in my acid. The other one has to be the acid. And the question is, which one of these atoms needs it the most? The best way to think about this, or actually there are two things you should look at. The first question is, which atom doesn't have a filled octet? Because when it comes down to it, the atom that doesn't have 8 electrons, which is the goal, will be the atom that accepts 2 more, right? That's going to be the easiest atom to give electrons to. It's the one that needs it the most, which doesn't have an octet. When we give electrons to hydrogen in a bond, hydrogen technically already has a bond, right? It has electrons. It's just a bad relationship. It's going to give something up. But I'd rather give it to an atom that doesn't need to give something up to take what I'm giving. That's the ideal situation. So if I look at this molecule, right, then I can see that boron, although it's neutral, it only has 6 electrons, right? Because it has 3 bonds. So you can tell very clearly that this boron is definitely the one that doesn't have an octet. The boron here has 6 electrons. So the boron's like, give me 2 more, give me 2 more. The hydrogen, the other thing you're going to look for is electronegativity. This is helpful, right? And we've been using that as an argument so far as to why we give it to the hydrogen, right? But in this problem, I would say it's very clear that the boron is the atom that needs it the most. And so as a result, I'm going to share these electrons with the boron. And guess what? The boron can accept those electrons and he doesn't have to do anything else, right? Unlike the hydrogen. If I had given it to the hydrogen in this case, I would have to break the bond that hydrogen currently has because hydrogen can't accept 2 unless it gives up the 2 that it currently has. And so because of that, we would end up with a product, right, that looks like this. Boron is now making a connection to nitrogen. It's still honoring its connections to the other hydrogens because they weren't involved in this electron sharing process. And the nitrogen is still making connections to its hydrogens because they too weren't involved in this sharing. The sharing was only between the boron and the hydrogen. And so really what happens is these 2 atoms just made a connection between each other. Boron doesn't need 8 to be neutral or to exist, but it will accept 2 more if you give it to it. And so now if I do my formal charge, the sticks plus the bond minus the valence electron minus the sticks minus the dots, boron is a valence of 3, nitrogen is a valence of 5, which means 3 minus 4 gives me minus 1. 5 minus 4 gives me plus 1. And so this would be the result of my acid-base reaction. I don't get 2 molecules because I did not need to break a bond in order for the boron to accept this. So you really have to evaluate this on a case-by-case basis. You can't just always expect the atom is going to break off from the atom it's attached to. It's really about electron count. Does it need 2 more? Does it not? If I want to give it to that atom and it has 8, then it has to lose 2. Or if it has 2 like hydrogen, then it has to lose 2. Okay? Do you want to try one on our own? I'm going to give you all a very, let's do a tricky one. Let's do something like this. Remember, you got to be careful about your H's. Your H's aren't always the acid. You have to look at the electronegativity difference between those atoms. I do have an electronegativity chart, in my in my in the folder. So let's see if you can do this one. Let's try to see what a possible outcome would be for these two reacting with each other. There's my equilibrium. And you can put your electrons on if you'd like. So what's a possible outcome? Which one is the acid and which one is the base? I think we all know which one is the base in this question. It must be the one on the right. I'm giving you a nice little negative charge. So that means this is the acid, right? Now, because we've broadened the definition where really a base by Lewis definition is just the molecule that's donating the electrons, and a Lewis acid is the molecule that's accepting the electrons. We have to define or figure out which atom in the acid is accepting the electrons. And so we have three different types of atoms in this molecule. We have H's that are identical, we have a carbon, and we have an oxygen. The question is, which of them will accept the electrons? And so in order to do that, let's go through the process. Let's look at the octet first. Does any of these atoms not have an octet? The hydrogen has access to 2 electrons. Both hydrogens have access to 2 electrons. And remember, for hydrogen, 2 is its octet. 2 is what it wants. It wants to get to 2, right? So a hydrogen is happy. Carbon has access to 8 electrons. So carbon also has an octet, right? Oxygen has access to 8 electrons. Oxygen is also happy. So we can't use the octet as an argument in this question for which one we're going to give the electrons to. So now we got to look at some electronegativity differences, right? Is there an electronegativity difference between 2 atoms that are bonded to each other? Is one of the atoms in a toxic relationship? Okay. Now we kind of need to know our electronegativities for this. And I think I gave you all a little bit of a sheet. I can tell you the electronegativity values if you don't have access to them. Carbon is about 2.5, hydrogen is about 2.1, and oxygen is about 3.5. Those are the electronegativity values for those atoms. So you can look at those and see which 2 atoms are going to have the largest difference would mean that relationship is the most toxic. Okay, so the C bonded with the O, yes, that's the worst relationship in this problem. Carbon and hydrogen are fairly neutral. Carbon to oxygen, there's a 1 point electronegativity difference. So now we know where the problem lies, right? We know that one of these atoms is willing to accept it because the other is hogging the electrons. So which one of the 2 atoms do we give it to? Do we give it to the one with the larger electronegativity difference, or the one with the one with that's more electronegative, I'm sorry, or the one that's less electronegative? Which one do we give it to, and why? Do we give it to the C or do we give it to the O? We give it to the carbon atom. And the reason why we give it to the carbon atom is because the carbon atom is the one that needs it the most. If you're in a toxic relationship, yeah, and your partner is hogging all of the money, right? Why would somebody else come inside and give the money to the person that's hogging it? You're going to give it to the person that needs it the most, right? Hopefully, maybe not. So I would say you should give the electrons to the carbon, because the carbon is the one that's suffering in that relationship, because the oxygen is more electronegative and pulling electron density towards itself. So I am a good Samaritan, and I want you all to be good Samaritans and always give the electrons to the atom that needs it the most. And that means this bond will have to break, because carbon can't accommodate 2 more electrons unless it releases 2. Because remember, we just said all of these atoms have filled octets. Hydrogen has its octet, which is 2, or duet. Carbon has access to 8, and oxygen has access to 8. So when I drew my bond or make my connection, I knew that whichever atom I gave it to, I would have to release 2 electrons from that atom. Does that make sense? Yes, maybe, kinda. Yeah. Okay. So that's how we do it. So do you see this process? You have to look at the acid and really think, which atom should I give the electrons to? And you have to evaluate that atom's need. If that atom is deficient, meaning it doesn't have 8, if it's a non-hydrogen atom, then you can just give it the electrons and everybody's all set. It'll get to 8. If it has like 6, for example, it'll get to 8. But if that atom needs it and it has 8, you just have to remember that you have to relieve one of its connections in order to give it. So what does that look like? Here is the oxygen now swinging around, right, and making its connection to the carbon, right? You can move it around however you want, and it makes its connection to the carbon using one of those lone pairs. Remember, that lone pair becomes a bond, right? And then one of the pi bond breaks because oxygen will get the electrons. Carbon has to maintain its 4 bonds, so it has to release one of its current bonds. And oxygen finally gets what it wants. It was already pulling those electrons towards itself, right? Remember, a bond was polarized this way because oxygen is pulling. And so now it gets what it wants, right? It gets the electrons it wanted, and carbon gets a bond from another oxygen. That hopefully is sharing it a little bit better. Okay, these are tricky, so why don't we try one more? How does that sound? Let's try one more and see. And these are going to be the 3 types of problems you probably will see when we get to when you move on and see other types of reactions. So here we have, and we're going to do the same base. This is our acid. Once again, our base. Oops, that's definitely not an acid. And that means this would have to be our acid based on this definition, okay? So which atom is going to accept the electrons? We have to look at these relationships. Let's be careful. I see a bunch of people saying Br, right? Let us think about which atom is in the worst relationship. We might need to pull up a periodic table for you all, but which atom is in the worst relationship? We have a base is going to give electrons to the other molecule. I don't know which atom is going to get it. I'm not drawing the line yet, but I have to decide which atom in that molecule is in the worst relationship. So the carbon and the hydrogen. Oh yeah, we can draw the lone pairs on the Br. I'm sorry. As I told you before, I don't always draw them because when I know they're there. So I'm going to probably make that mistake. But yes, the bromine does have 3 lone pairs. It has to have 8 electrons. So let's look at the relationships. Carbon and hydrogen have pretty much the same electronegativity difference. Yes. So they're probably going to be okay together. What about carbon and bromine? What about that bond? Which one is more electronegative in that relationship? Is it carbon or is it bromine? It's going to be the bromine. Bromine is more electronegative. It's further to the right of the periodic table. And so the carbon is the one that's suffering. Yes? Does that make sense? So the atom that's not less electronegative is the one that's suffering. So I want to give electrons to that atom. Okay? That's the atom I always want to give electrons to. And because the carbon already has 4, it has to give up 2 to the bromine, which is pulling it. So it's a very similar concept. If you think about it this way, you can really draw any reaction. It doesn't have to be acid base, it could be anything. And this is a good example of a reaction that we call a substitution reaction. This one is specifically an SN2. And you've never seen this reaction before, ever. But the idea is if you understand just some concepts about electronegativity and octet rules, then you could potentially draw a reasonable outcome for two molecules interacting. And the reason why I say suffering, actually, is this. Let's maybe go back a little bit to this. Here is carbon, here is bromine. Here is carbon, here is oxygen. This bond exists, these bonds exist between these two atoms. If we look at our periodic table, right, and I will draw a simplistic version of one, then the atoms on this side of the periodic table are very electronegative, okay? They are pulling electrons that are shared in that bond towards itself. So the bromine is over here and carbon is over here on the periodic table. So that means that bromine has a stronger pull. You need to think about these bonds as tug of war, right? These bonds are in a relationship. The electrons are in the rope between them, but it's not an even bond, right? It's tug of war. And the atoms on the right of the periodic table are always going to win that tug of war. They're really pulling those electrons towards themselves. So that's why I use the word suffering, because carbon is just not as strong as bromine. So the electrons in this bond, they're really closer to bromine than they are to carbon. They're probably more over here if we look at it as a picture, right? Or make a picture of it. And so the carbon is kind of suffering because it's not really having good access to those two electrons that it really wants to hold on to complete its 8. Because presumably the carbon has 3 more bonds. Does that make sense? So the carbon, when it's bonded to something, any atom, when it's bonded to something that's more electronegative, is going to be suffering. Those electrons it won't have full access to them, okay? And so that's what's going on here. And so let's finish this up and draw the product here. The product then is the carbon is going to be now attached to the oxygen that's attached to the carbon, the oxygen to the carbon to the OH. Remember, the H is coming along with the O. And then the bromine is going to now be by itself. And so this is the outcome of that reaction, as you can see. Basically, we call this a substitution because we really are substituting the bromine for the OH. And that gives you a new product and a Br minus. Okay? And yes, OCHEM, solving literally one toxic relationship at a time. I like that. Okay, so that's Lewis' definition. We did a lot of these. I'm going to put a bunch in the drive so that you all can work on them this week. All right, resonance. Oh boy. I'm sorry, but today's lecture is a little tough. We have some tough concepts that we have to get through. And we'll probably end it at resonance. Okay. So what is resonance? Resonance. Oh, I saw a question on the board. Not every acid-base reaction you have to generate water. Typically in the Bronsted-Lowry ones you've seen, you probably will generate water if OH minus is your base. But this was not a Bronsted-Lowry interaction. We weren't removing a hydrogen. We're actually interacting with a carbon, so you couldn't make water in that particular case. All right, resonance. So when we look at a molecule, we have to realize that the electrons in a molecule aren't permanently in the place that we draw them. A Lewis structure is kind of not a very good depiction of a molecule. And that's because electrons aren't static, right? Just like the platelets and in your blood and your red blood cells, they're not in one place, right? They're just constantly moving through your body, right? If you take a snapshot of your body, if you could like label all of your red blood cells, one through however many trillion of them we have in our body, we would be able to take a snapshot of our body. If we could, they would be in a different location, right? Constantly. And so the same thing happens with electrons. And that is the electrons aren't always in the same place. They can sometimes move throughout the molecule. And so when we draw a Lewis structure, it really isn't a perfect representation of the molecule because it's not giving you any idea about the fluidity of the electrons, right? And so what a resonance structure is, it's an attempt for us to get a better understanding of where the electrons are or where they could be at any given time, right? And so what we have to get good at is to be able to draw that or to anticipate where electrons are or how they can move throughout a molecule and end up somewhere else and move back to that other place, right? So we're kind of getting their motion down pat. So what this requires, and the reason why I did the acid-base reactions first, is because we have to really appreciate how electrons move. And to appreciate how electrons move, we have to know about the octet, right? We have to make sure that all the atoms have octets, and we're trying to make sure that 8 electrons, not 10, right? That would be too much. And so having an appreciation of that will allow us to show how electrons can move. So really, there's really some 3 rules I like to tell people when they think about how to derive a resonance structure from an already given structure. And that is this: you should really only move lone pairs and pi bonds. So double bonds and lone pairs are the only things you should move. And that's because if I have a molecule like this, okay, and I say, for example, try to move these electrons to the hydrogen, okay, what I've done here is that if I move this atom, I have broken that bond, right? I have literally broken that bond. These 2 atoms are no longer attached, okay? And the idea is not to break the molecule apart, it's to show the electrons moving through the molecule, right? So that's not a possible way electrons would move in this molecule, because that's not moving through the molecule. You're actually destroying the molecule or breaking the molecule into pieces. And so we never move single bonds when we're trying to show molecules moving, through a structure. The other thing is, as a result of that, yes, I'm sorry, you only move double bonds and lone pairs, but we never break, as I'm showing you, single bonds or create new single bonds. And the final thing is, the overall charge must remain the same in one structure compared to the other. So let me give you an example now of how we can do that. It's just best if we do a problem, okay? Let's do a problem and let's see. Here's a molecule that I know can have a resonance form, okay? This molecule, I can in fact draw it in a different way. I can show the electrons in different places in this molecule. So let's think about how we're going to get that. I always suggest you start at the place of high electron density, right? If I'm going to move electrons through the molecule, they're probably going to be moved from a part of the molecule where electron density has been built up, right? So it's obvious to me that electron density is built up on the right side of this molecule because I have a firm negative charge on my oxygen, right? So that is an area of high electron density. So I'm going to start there, right? I'm going to start to move my electron density from there and see if I can make electrons move to another location in the molecule. Let me put all the electrons in. I always forget to do that. So how can I move electrons through this system? Let's think about it. Let's think about them as neighbors. These are all atoms living on the same street, and they have electrons attached to them, okay? So what can oxygen, are we all in agreement that the oxygen atom is the atom that is the most electron rich based off of our observations here. Yes, we're in agreement. Oxygen has a negative charge. Good. So what can oxygen do if it wants to move electrons through this molecule? Oxygen could do what? It could share those electrons with its neighbor, right? Oxygen could share with its neighboring atom, which is a carbon. Yes? Everybody's in agreement? Let's also be clear about this process. You do not want to give electrons away. You can't do that in a resonance, okay? You're not going to throw the electrons from one atom to the next. If you want to move electrons from one atom to another atom, the only thing you can do is to share them. No, that's my rule, okay? You can only share them with your neighbor. You cannot just throw them across from one atom to the atom. So you couldn't just take these electrons, okay? You couldn't just take those electrons and just toss them across the way. You couldn't have just take those and just throw them on there. Does that make sense? You can't do that. That's not allowed. You can only share them, okay? So let's share them. If I'm going to share them, this is how I would share them. This has to go in between, right? If I have electrons and I'm like, hey, carbon, do you want to share my electrons with me? Then carbon has to be like, yes, put them in between, all right? They have to be shared in between. So that's how you move electrons. So let's draw the result of those electrons. We're doing this slowly, very, very slow, okay? This will make sense in a second. So hydrogen, oops, is sharing those electrons with the oxygen. So do you see what we just did? We took those electrons here and we move them in between. Remember, when you move electrons in between, that's just a bond, okay? Electrons in between two atoms is just a bond. So we're making a bond. Yes, do we agree? That's all we're doing. We are making a bond by sharing them. Now, a problem has been created in doing that. As much as this oxygen is being generous and it wants to share with its neighbor, a problem is going to be created if it in fact shares electrons with its neighbor. What is the problem that we created by sharing this? What happened to the carbon? Too many bonds on carbon. Someone said it. Exactly. If I share the electrons with the carbon, I've made too many bonds to the carbon. So, can I still share electrons with the carbon? I can share electrons with the carbon, but the carbon has to do something to accept them. What does the carbon have to do to accept them? If the carbon's going to accept these electrons, right, then it has to release two electrons that it currently has, right? It has to drop a bond. It cannot maintain all of those bonds, right? So let's make sure we draw this in another picture, right? So here are the two electrons that it just gave, okay, to the carbon. But the carbon can only accept it if it gives up these two electrons, okay, and remain at 4 bonds. And so what would that look like? Let's redraw this. Let me draw this with a different color so we can see. And that's okay because oxygen can accept those electrons. So if we redraw that process, that seems like a likely process to me now. Then what we have is oxygen up here will now have an extra electron and it will be negative. And the oxygen on the bottom right will have two lone pairs and 2 electrons and two bonds, which makes it neutral and 0. This is an example of a resonance structure. And you can see the reason why they're resonance structures is because the electron density has shifted, right? In this structure, this atom was negative, but in this structure, it's that atom that's negative. So we've literally moved the electron density from the right side of the molecule to the top of the molecule. And that is a resonance, but it's the same molecule. The electrons are really just in a different place. The carbon still has a 4 bonds, 8 electrons, and the oxygens all have respectable electrons that they can accommodate. And the hydrogen is left intact. Does that make sense? So what's happening now, though, is that this is a constant process that is happening, where electrons can be moving from one side of the molecule to the other side, and they can move from that side back to the other side. And why would this happen? Think about it. Hot potato, right? If you think about electrons as a hot potato and your hands as the 2 oxygens, you can just share that burden between those 2 atoms. You hold electrons now. I'll hold electrons. You hold electrons. I hold electrons, right? So it's a nice way to share that charge and to stabilize the molecule from being too electron rich. And so why don't we try to draw the resonance going in the opposite direction? Let's draw it from the other one. In this case, this oxygen at the top is the one that is electron rich, right? So that could share electrons with its neighboring carbon. But once again, in doing so, we're going to create 5 bonds, right? We're going to create another bond to carbon. And in order for carbon to accommodate that bond, that carbon too has to lose electrons from itself. Remember, we only move electrons and pi bonds, and so the pi bond is going to break. And of course, the natural place for it to give the electrons is to the oxygen, because the oxygen is electronegative. And if you draw the result of that, you end up exactly where you started, in the structure on the top left. You end up right back here. And then you could do the same thing the other direction, and you end up here. And so they're really just going back and forth. It's going back and forth, back and forth, back and forth, back and forth. And that charge is just moving from one side of the molecule to the next. And a lot of molecules have this ability to do that, to move electron density through the molecule. Okay, let's try one and see if you can do this. Here is another simple one. This time the oxygen is positive. What could we draw? This one's a little hard. So I will, well, not really, but I will give you some advice. So if the molecule you have has a negative charge in it, that's where you want to start, generally speaking. I'm simplifying a bunch of stuff here, but that's a good approach. If there's a negative charge in your molecule, that's kind of where you want to start moving electrons. What do you think it means if there's a positive charge in your molecule? That's kind of where you want to end, okay? You want to typically move electrons towards the positive charge, and you want to also move electrons away from a positive charge. So for me, when I'm trying to draw a resonance, if it's possible, and there's a positively charged atom in my molecule, that's kind of a goal for me. I'm going to try to see if I can move electrons to the positive charge. On the other hand, if I have a molecule that has a negative charge, I'm going to try to see if I can move electrons away from that negative charge. So I kind of have a starting point or an ending point, right? That's kind of the goal here. All right, let us see if we can find electrons and move them. What electrons could we move to the positive charge? Remember, we cannot break single bonds ever, right? So we can move the electrons from the pi bond. We can only move electrons, not atoms, only move electrons. And so the only electrons, these are our options. We have 2 electrons here. We have 2 electrons here. We have 2 here, 2 here, and 2 here. This idea of resonance is we are moving electrons, okay? Only electrons. The atoms must stay in the same place. And so that's correct. We can move the pi bond, yes, the electrons in the pi bond to the oxygen, because the oxygen is the one that's positive. and we can move the electrons to the oxygen, and the oxygen will get two more. Let us draw what that looks like. The oxygen still has the H. Do you notice the atoms are exactly where they were? We don't move the atoms, just the electrons. And so I gave the oxygen two more. Those electrons in that pi bond are two electrons. And so we end up with this product, okay? Now let's evaluate if anything has a charge, because remember I told you in the third bullet point that the overall charge must remain the same in all resonance structures. So let's go through. Is any atom unhappy in this molecule? Yes, the oxygen has 8 electrons in neutral. The carbon needs a charge. The carbon only has 3 bonds, which based off our math, valence minus the sticks, 3 sticks, must mean that the carbon has a positive 1 charge. And therefore, both resonance forms are good, right? There's one single positive charge on the left molecule and one single positive charge in the right molecule. And so this is a good resonance structure. Well, not excellent one, but an acceptable resonance structure. And so this is how you do it. Now, what I think I'm going to do on Tuesday for our class is we're going to really just spend some time doing like half an hour doing a bunch of these again. And then I'm going to give you a test. Legit, I'm going to post a test on the screen and you're going to have to do it and see how far you get. And don't be sad if you don't get everything right, but I'm going to have you all identify functional groups. I'm going to have you draw Lewis structures, and I'm going to have you draw acid-base reactions. And I'm going to have you draw a resonance structure, because that's all we've done so far. These are kind of like the amazing intro stuff that you need to learn. And so I'm going to test your knowledge on all of these. Okay, does that sound good? And so I think we're going to end here for tonight. Time flew by. Yeah, you learned a lot of stuff today. And I'm going to put up a bunch of problems in the drive for you to practice, and we'll do some more. And your guys are well on your way to becoming organic chemists. All right. So thank you all for stopping in again. And I'm excited to see you all on Tuesday.